You walk up, drop in a coin, pull a lever, and you get what you paid for. The physical interaction feels instantaneous, but behind that casing is a dense mechanical labyrinth. Columns of tightly packed products, levers, and coin slots all have to work in perfect synchronization. The wild part about classic machines like these is that they calculate change, track product inventory, and verify currency without an actual computer processor. There is no CPU inside making decisions. Instead, their entire operation is governed by a network of simple digital logic gates. To see exactly how that works, we are going inside a digital simulator called Logisim-Evolution to build a vending machine's logic circuit from the ground up. We will track the precise journey of a single transaction, from the moment a coin drops into the slot to the second a snack drops into the tray. You'll see how physical actions are translated into digital logic across 4 isolated, interconnected modules. Tracing this microtransaction reveals how simple logic gates combine to perform a complete, automated task. The entire process kicks off the second you drop a coin into the physical slot. The object drops into the bank subcircuit, where a binary encoder translates the coin into a distinct binary number. An adder circuit continuously calculates the running total. Finally, an edge-triggered clock signal pulses, locking that sum into a register memory bank. That specific combination of adders and precise clock signals gives an otherwise inanimate machine short-term memory. To make a purchase, the machine requires you to hit a hard-coded threshold, in this case 75 cents. Here, the Activator subcircuit takes over. A comparator block constantly weighs your inputted memory balance against a static value of 75. Once the balance meets or exceeds the purchase price, the comparator registers a match and fires off a solid enable signal. If you happen to overpay, a dedicated subtractor circuit instantly kicks in to calculate the exact amount of required change. By comparing 2 simple values, the Activator acts as the absolute gatekeeper for all physical movement in the machine. With the payment cleared, you press the button for your chosen product. Deep inside, this diagram visualizes a demultiplexer taking your specific button press and routing the incoming electrical signal down one of 3 branching paths, directing it to the correct product subcircuit. That signal hits a D flip-flop, triggering a short, highly active electrical pulse to the physical actuator. The metal coil spins, and your snack drops. Simultaneously, a digital counter operating in the background subtracts exactly 1 item from the machine's internal inventory. If that specific inventory counter ever hits 0, the logic trips a physical sold-out LED to warn the next person in line. These isolated modular boxes, the bank, the Activator, and the dispenser, wire perfectly together to form the main circuit, turning a physical coin into a physical snack. In a controlled simulator like Logisim, that process looks perfectly clean. But human users are unpredictable, and theoretical logic often collides with reality. During the initial testing phase, 3 critical flaws emerged. The machine would accept an infinite number of coins, it forgot to wipe its own memory after a sale, and it completely lost track of the total daily profits. To fix this, engineers added hard caps. The diagram shows a block dropping onto the data stream at 75 cents, rejecting further input. For the second flaw, reset lines were installed. A signal flashes, instantly wiping the balance to 0. Making a machine work is only half the battle. Real-world engineering is about strictly defining a system's boundaries so that it cannot be broken. So, the next time you walk past a vending machine humming quietly in a hallway, remember that it's actually a system of modular subcircuits, each one dedicated to one specific stage of the transaction. From smartphones to global internet servers, all modern computing relies on this same strategy, breaking massive problems down into small, perfectly timed digital logic circuits.